So review number 8 is actually on, as you'll see on the top here, review number 9. Number 8 was the parametric vector information that is not on this year's test. So we skip that. We have number 9 to get done. You'll see at the top deals with differential equations and logistic growth. That also, gets into Euler's method and slope field. So that's going to be the main theme throughout this packet. So one of the things that is not uncommon is they'll give you a differential equation, have you sketch a slope field, and then line tangent Euler's method, and then separating variables to do the antiderivative. So use a differential equation with initial conditions y of 2, answer these first 3 questions. First thing, you're just going to sketch this. They typically will just give you a handful of dots. You don't have to do it for an entire slope field. And if you remember, all we really did, so we would go to a certain point. So let's take the point 1, 1, and we would want to figure out what's our slope right there. So at the point 1, 1, your derivative is always x squared times your y value. So this would be 1 squared times your y value of 1. We'd have a slope of 1. So if I do a slope of 1, if you remember, there's no way for us to actually measure that to be exact. But then just keep in mind, like if I go up to the point above it, 1, 2, that slope would be 1 squared times my y coordinate of 2. If that slope is a value of 2, that one better be a little steeper than the one that we know is a slope of 1 below it. If we come over here to a negative 1, 1, and find that slope, that's a negative 1 squared times your y value of 1. That's also a slope of 1. So if this was a slope of 1 and this is a slope of 1, they should resemble each other. Pretty darn close to being the same. And then same here. If this is a negative 1, 2, so I do a negative 1 squared times 2, that's also a slope of 2. So it should be steeper than the one below, and it should be similar to the one that we also said is 2. Any of these values, when x is a 0 at all of these points, then your slope is going to be a 0, so we would draw those and so on and so forth. And I assume you can kind of do those. Same thing when we start getting those negatives. All right. Euler's method. So here's Euler's method. Let me make this a little bigger so I can hopefully fit all of this in here. Is when we would do, so first, let's go through the problem. We know at the x value of 0, our y value is 2. The question is asking us to approximate when x is a, let me try this again. So when x is a 1, what's our approximate y value? So we have to go from 0 to 1, and our step size is going to be 0.2. Actually, you know what? If you're watching this, let's simplify this a little bit. They would never have you do this without a, suppose if you can do this without a calculator, they wouldn't have you do too many of these. Honestly, I've never seen them make you do this more than 2 times. So instead of saying y of 1, let's do this. Keep this short and sweet because it's about as many times they'd have you do it. Let's say y of 0.4. So I'm going to start at 0, and we want to ultimately figure out what's my value at 0.4. And we're going to go with a step size of 0.2. That means we would have to do 2 steps of Euler's method to go from 0 to 0.4. So Euler's method, if you remember, if I want that first approximation, what we did is we used our initial y value plus the derivative at the initial points, so I'll write it like this, multiplied by whatever the difference in x is, whatever our step size is. So for this problem, the original y value that we know, y sub 0, is this 2 right here. Then we would need our derivative at that point. The derivative is up here again, x squared times a y. So for this problem, we would do 0 squared times 2. That's x squared times y. That's the derivative at the original point. And then we would have to multiply that by our dx. Our dx is this 0.2. We would then evaluate that. This is a pretty simple one because this would be 0. You're going to multiply 0 times a 0.2. So you really just end up with a 2 plus a 0. So our first y value that we would get is 2. Remember how we kept track of our points? Now that I have that here, let me erase this. What we are now at is the point 0.2, 2. So our new y coordinate is 2. We started at 0. We moved over 0.2, so now that's our new x coordinate of 0.2. Y sub 2, we now use the new y value here, 2, plus the derivative at our new point. And so if you remember, it's x squared times y. X is now that 0.2, and then our y value is still 2. So that's our derivative value. And then times our step size, dx, of 0.2. That I'm going to need to plug in here so I don't mess this up. So give me a second. All right, that, if I plugged it in correctly, is 2.016. So now this is y sub 2 would equal this. Euler's method is similar to a Taylor polynomial or Taylor series. They expect you to use the approximation symbol. So the way we would want to write this is we would now say y of 0.4. Actually write what we're looking for, y of 0.4. Don't leave it in terms of y sub 2, the line, is approximately, and then we would say 2.016. What they typically then follow that up with is, let's find the real value. If this is our approximate value, let's change this again. Let's find the real value at 0.4. So, and then we'll be able to use an equal sign for this one, because if we can actually find the original function, plug in a 0.4, then we know that's going to be exact. So that's going to be our process. So dy dx for this problem is x squared times y. If we're going to find the exact value, we need to figure out what the original function is. So if this is your derivative, this is when we separated our variables, we multiply the dx over, divide the y over, and go through that process. Once they're separate, you're going to do your antiderivative. This is our natural log of y. This would be x cubed over 3 plus your constant. Let's solve for c. The way we can solve for c, if you go back up to here, where I gave you this, when x is 0, y is 2. So I'm going to let my y be a 2. Let your x be a 0, so we know c is the natural log of 2. So I can now write my equation that I had before, and instead of having to use the generic plus c, we know that our c is now a natural log of 2. To solve for the y then, we're going to use our e. So these will cancel. Remember our shortcut here, I know we've talked about this a little bit in some of these reviews. The reason you're adding exponents is because you would have been multiplying like terms of e. That would have caused us to add those exponents. These then would cancel. We get 2e to the x cubed over a 3. Now that I have that, I can actually figure out what is my exact value. Oops, not at 2. Darn it. But now I can use that equation and figure out my exact value at 0.4. So again, give me a minute. Let me plug that in. And what we will get is 2.043. So you'll notice these are quite similar. They should be. One's an approximation, one is exact. So, and we didn't move too far away from 0, where we're tangent to the curve. So those should have been pretty similar. We talked about it a little bit, if you recall. When we have a curve that is concave up, our line tangent is below. If we have a curve that's concave down, our tangent lines will always be above. So if I have an approximation here that's smaller than the real value, which is how this one played out, that would mean my curve would have been concave up at the value that we're approximating it for. All right, number 4. Yeah, this I had to download from, so I don't have to do it in a PDF, so it doesn't format great. So change yours. This should say dy dx would equal a negative 2x over y. So fill that in. Hopefully not a big deal, but it allows me to do this in Word and a little less stressful, and I can actually make this a little bit neater. So slope field again, we'll do one or two of these just as a little refresher. Let's do some negative ones in this case. So let's come down to the point 1, negative 1. Now your dy dx, your slope, is always a negative 2x divided by y. So we would do a negative 2 times 1, and then my y value is a negative 1. So the slope at that point is a 2. So the initial one is a 2. If we go below that, so now let's try if I can fit this. 1, negative 2. My slope would be now negative 2 times 1 divided by the y value of a negative 2. Now my slope is a 1. So if this up here was the 2, the slope of 1 shouldn't be as steep. All right, a little flatter. And then we just work our way around. Anytime x is a 0 again, you're going to get slopes of 0. I come down to these negative values, negative 1, negative 2. My slope is the negative 2 times my x divided by the negative 2. So that make you think a little bit. Negative 1. So now my slope is a negative 1 here. If I come to this one, this is the point, what, negative 1, negative 1. So a negative 2 times the x divided by the y. So that should be a slope of a negative 2. So negative, a little steeper than the one below it. All right, so that's our slope field. B. I put these back to back, B and C, because almost every year people come back and I hear people make this mistake. B says let f of x be the particular solution, as does C. The particular solution is y equals f of x. So the original function is our solution. Letter B is asking you to write an equation for the line tangent to the curve. Letter C is actually asking you to find the curve. So this is line tangent to curve. This means you actually want the curve. So two completely different ideas, and it's not that difficult on that day with all the stress and everything to get those two things mixed up. So if we want a line tangent to the curve, that's pretty straightforward. We need a point. You are given your point, 1, negative 1. That's right there. So we have that. And then the second thing we always talked about is what is our slope at that point. So we would need our derivative value at 1. Of course, we didn't do that one over here, but we would have already had that one if we would have done this point in the slope field. Our slope would have been a negative 2 times the x coordinate divided by the y coordinate. So that slope would have been a negative 2. We can then write our equation. Let me go ahead and simplify this. We got negative 2x plus 1. That's our line tangent. And then once we have that, we're going to use that to evaluate or approximate the value at 1.1. So y of 1.1 would be negative 2 times 1.1 plus 1. And then we would want to present this as an approximation, the approximate value for f of 1.1 using our line tangent would be a negative 1.2. C, find the particular solution. So if the function is the solution, they want you to find the solution, they're really wanting you to find that function. So similar to the one above, let me write this. Our differential equation was dy dx equals a negative 2x over y. Whoa, that's cool. Not sure why they did that. Let me fix this. Separate our variables. Once they're separated, we do our antiderivative. We'll find our C. The reason they gave you a point here is to figure out your C. The reason they gave you that same point here is to figure out what the line tangent was. So they give you that in both instances. Do we want a line tangent or do we want the curve? In this case, we wanted the curve. So plug in the y value, negative 1 squared over 2. And then that equals a negative, and then the x gets plugged in. I don't know why that's kind of neat, but I don't know why it's doing that. We can then figure out what our C is. This would be what? C would equal, this would be 1/2, add the -1 over. So C is 3/2. Now go through, solve for your y. So multiply everything by a 2. Take our square roots. Keep in mind that we don't, in our final answer, want to have the plus minus. What should happen here is I should be able to plug in a 1, and I better get a -1 for my answer. So here's what I mean by that. If I were to keep that plus minus there, think about if your x is a 1. What this would give you is a positive and a negative. Underneath the radical, that's going to evaluate positive and -1. Well, we don't want it to be a positive and a -1. We only want it to be a -1. We don't want this here. We don't want this here. So while this is sort of your answer, we actually don't want the positive there. We need that to be the negative root -2x squared plus a 3 so that it would satisfy this initial condition up here that when x is a 1, y is a -1. Okay, so pretty tricky there. Just be careful of something like that. All right, next page, if I can move you. Number 5, using Euler's method with a step size of 0.25, estimate f of 1. Given these conditions, we're going to change this again. There's no way they're going to have you do this free response wise, especially on a short test you would never finish. So let's take this and let's again just do f of 0.5. That way we understand if we're starting at x equals 0 and we get a y value of 2, that's what this tells us. And if I want to ultimately get to 0.5 to figure out what is my y value at 0.5, in order to go from 0 to 0.5, with this as my step size, I should only need to do 2 of these. So Euler's method is this. So for this problem, my initial y value is 2. Then I would need my derivative at that point. The derivative is the y coordinate minus the x coordinate. So knowing the point that I'm starting at, I'm doing the y coordinate of 2 minus the x coordinate of 0, and my step size is 0.25. So that would be what? 2 plus 2 times 1/4 is 1/2. So the first value we get is 2.5. Over here, we kept track of where we are now at. We know for sure our y value is 2.5. We just found that. But if I had started at 0, which I did, if we come back to here, and my step size is 0.25, that means my x coordinate is the 0.25. So we would do one more. The new y value is the 2.5. Plus the derivative, so same formula, y minus x. We're just using this point now. So we would do the y coordinate of 2.5 minus the x coordinate of 0.25, and then our step size is still that 0.25. Evaluate that, and we should get 3.0625. So my approximate value for the function at 0.5 should be 3.0625. 6, we've already mentioned it a little bit. Using Euler's method, if it's less than the actual value, that tells us that we are concave up because we're stringing these little line segments together. Okay, it's like a better approximation than line's tangent. So if the curve is concave up, our line is underneath. So the Euler's method approximation is less than means our curve is concave up. 7, just another one where you're given your differential equation. We separate those variables. So multiply the dx over, divide the y over. So that should give us this dy over y equals 1 over 2 root x times your dx. We would do the antiderivative of both sides, so the natural log of y, let's bump this guy up so it's a negative half power. So that would be 1/2 times x to the 1/2. Divide by a half, but let's really just multiply that by 2, plus your constant. Then we'll see those will cancel. So we have the natural log of y equals, or root x, and then plus our c. I'm going to find c, so I'm going to use this point to do that. The natural log of y is the natural log of 1 in this case, and when y is a 1, x is a 4, plus your constant. Natural log of 1 is 0, so we get c to equal a negative 2. So now we can write this equation, this natural log absolute value of y equal to a root x minus 2, and then use your e, and we should get that. All right, e to the root x minus 2. Sometimes we play little games with this, but in this case we can look. That's how letter e is written. That's your final answer. 8, the curve that passes through the point 1, 1 and whose slope at any point is equal to 3y over x has the equation. So this is one that we mentioned earlier. It's really, really easy. Every year people come back, like I mentioned, making this mistake. In number 8, ask yourself, do I want the line tangent to the curve, or do I want the curve itself? And then that's going to guide your decision, because they set up very, very similar, where they're going to give you a derivative, they're going to give you a point. Are we given that point to write the line tangent, or are we given that point to find a c? So in number 8, nowhere in here do you read the words lines tangent to a curve. All you read is the curve that passes through this point whose slope is this is equal to what equation. So we are looking for the equation of the curve, not a line tangent to the curve. So it's written a little differently. Keep in mind the slope when they use, or I use the word slope, that is your derivative. So it's the exact same type of problem that we've now done a few times today. You're going to separate your variables, so multiply the dx over the y and the 3. The 3 does not have to stay with your y. I would actually strongly recommend not moving the 3 over. No need to create a fraction if we don't already have one. Do your antiderivative of both sides. We get a couple natural logs here. The reason you were given that point is to figure out what your c was, and this works out very nicely because all of the variables become a 1, which means everything becomes a 0. So your c is just a 0. We can then write this as the natural log of our y, absolute value, equal to 3 natural log absolute value of your x. If we're solving for y, we would use our e. That's going to cancel. But remember, that e and natural log cannot cancel yet. We would first need to take this 3 and make it the power x, and then now they're going to cancel, and we're just left with y equals x cubed, which is c. 9. We did this a little bit the other day. I doubt you would have to really worry too much about number 9, where you're given the whole dy dx equals ky, or dp dt equals kp. Same thing with just some different variables, where a population, so the change in population over a change in time, the way we can figure out that rate, that growth, is to take the constant k with rate, multiply it by our population. When we did that, we always got this population equation. That's the exponential growth model. That's an AB topic and a BC topic. D is the BC specific topic, so you're more likely to see this one, especially this year, where you're given this differential equation. So this should be our differential equation. This should actually be a t, so change this to a t. Little k is your rate, and actually let's change this to a p, sorry. So dp dt, so the change in population over a change in time, is equal to this constant rate of k. P is our population at whatever time we're concerned about. Capital K is our carrying capacity. We integrated that at one point. It was a really long, messy process, and when we did that, it will always produce this population equation. So this is kind of like our velocity. This one is your position, if we want to equate it to things that we're more familiar with. So velocity, population. K is your carrying capacity. The way we figure out our A, so again, this didn't convert very well, so let me just fill this in. The way we figure out A is K, your big K, so your carrying capacity, minus your initial population divided by your initial population. That's what this should say here. And then we'll do one or so, and then catch the hang of this in case we see it. So 11, suppose that a population grows according to the logistic model with a carrying capacity of 2,000 and a rate of growth K that's equal to 2.5%. All you're doing first is writing the logistic differential equation. So that's this version. So we would say dp dt would equal, little k is your rate. We know what that is, 0.025. P, and then 1 minus P over K, capital K. That is your carrying capacity of 2,000. That's all you would be doing if that's what that question asked for. B, the initial population is 750, so that means at the time of 0, our initial population was 750. Write a formula for the population at any time. That is this version. So now we would say my population at any time would be the carrying capacity, which we know is 2,000. We don't know A just yet. We're going to figure that out in a minute. E to a negative KT, so the little k we know, plus a 1. So A we don't know just yet, but what we are given is a way to figure out what A is, and that's this formula here. A is your carrying capacity of 2,000 minus your initial population of 750 divided by your initial population of 750. Whatever that evaluates to be is going to be our A. Divide by 750. Yeah, and that's 5/3. So my population at any time would be the 2,000, and then 5/3 e to a negative 0.025 t plus a 1. That's a 3 right here. Okay. 12. Spread of an infectious disease to workers on a large floor in an office building is given by, and then that is your population equation in the logistic model. T is the represents the number of infected people. What is the growth rate in infected people per day that the disease exhibits when it is spreading fastest? So when the question is asking what is the growth rate, that's basically our derivative. So if this is your logistic population equation and it's asking what is our growth rate, what is dp dt, then we could hopefully jump right to that, where if we can kind of remember what all of that was, little k times p and then 1 minus p over the big K. Let's fill in then the things that we know. So little k, we can look at this equation up here. Actually, be really careful with little k because the formula would read e to a negative kt. So we have our e here, negative kt. The fact that that's a negative 1/2 tells you that your k, little k, is actually a positive half. And then our population, 1 minus our population, divided by our carrying capacity. By looking at that differential equation of this model, we would know is 200. This is one thing we hadn't really talked, I guess, I don't remember. We may have talked about it, we may not have. Sometimes I talk about it with some classes, sometimes I forget in another. When it asks you this question, what is the growth rate infected people today that this disease exhibits when it is spreading the fastest? So think about the logistic differential equation, the model. It starts out growing exponentially, which means it starts growing slowly, but then eventually exponential graphs grow very, very quickly. But eventually we talked about how we can't continue to grow exponentially forever. Eventually we're going to start to approach our carrying capacity. That's what the logistic model looks like. The time when we are growing the fastest, when we have to stop growing exponentially, is when half the people, so think about the rumor. In each class, we started a rumor about somebody in 6th and 7th period. If I tell 2 people, they then tell 2 people, we can grow exponentially. Eventually, we can't grow exponentially anymore. And when that would start to happen is when each person no longer has two people to share anymore, because as many people know the rumor that no longer know the rumor. So what that pretty much is telling you, and this is something you just want to know, we are always spreading the fastest, so write this down, when we are 1/2 of our carrying capacity. If we know our carrying capacity then is 200, that's the population that we want to be evaluating this at. So we would want to be figuring out our derivative value evaluated when our population is 100. All right, so that would give us what? 50 times 1/2. So that we would get 25. 13 and 14, we'll do one or two of these. If you've looked at the AP question already, you'll kind of see what's happened with these. Plot the point 0, 1. I'm going to make this bigger, I think, hopefully, so you can see better on these. So if I plot the point 0, 1, that would be right here. We want to sketch the solution curve that would go through this. So this one seems to be pointing pretty good to here. To me, this one, I'd have to skip this line. I'd probably skip the second. So I wouldn't do this line at all. I would skip this line as well. Next one I would probably go to is the one up here. If I could draw this in nice. Well, maybe I would inadvertently. Hard to control this little guy. It's slippery. And then this one would swing down here. That would be our graph. If I plotted the point -1, -1, that would be right. Let's make it here just so there's an actual point. Should kind of tumble like this. All right. If we do 2, 0 over here, here's 2, 0. Looks like we level off and then kind of create this diagonal line here. -1, -1. If you wanted to pause me, try to do one of these. So -1 is here, probably this point. Yeah, -1. Yeah, this is weird how this is labeled. And it comes down here. All right. 15. Oh boy. You know what? I'm not even going to write those because you don't have to do multiple choice. So there shouldn't really be any multiple choice questions on here, which means they'd either have you create one of these, which we did on the front page, or they would have you sketch in a solution curve to one of these. So we're going to skip 15. We'll save everybody a little bit of time. Same with 16. All right, same with this one. I think the multiple choice stuff we can not worry about. And since it didn't format well, we're not going to concern ourselves with it, which makes us done. Perfect. So that's, differential equations, slope fields, Euler's method. Those very, very commonly all go together. We'll call that a day. There is one more review. That's the most recent topic. That's the Taylor series topic. I'll try to get that up here in the next few days, but you have all that information. It's the freshest in our head. The reason I make that kind of the last review packet is if we can't get it done at night, it's the stuff that we just got done looking over. So with that, I'll see you guys later. Have a good night. And again, let me know if you need anything.